On the morning of August 27, 1998, a tanker truck hauling industrial rubber accelerant rolled over on a highway in southwestern Virginia, 500 feet from the Clinch River. 1,350 gallons of a chemical called Octocure 554, a dense zinc oxide compound used in the manufacture of foam rubber, poured through a drainage ditch and hit the water. The river turned snowy white. Within hours, the chemical had burned through a 7-mile stretch of riverbed, killing every mussel, every insect larva, every living thing anchored to the bottom. Biologists walking the banks in the days that followed pulled 6,207 dead mussels off the surface of the gravel. But mussels die buried, clamped shut beneath the cobble where nobody can count them. The real figure, accounting for what they could not see, came to 18,621. Three of the species killed were already federally endangered. One of them, the golden riffle shell, had only two known breeding populations left on the planet. The spill erased one of them in a single afternoon. Some of the individual animals pulled from the gravel were 80 years old. And 2 years before that, the next river over had already taken a hit. 6 million gallons of toxic coal slurry had blown through a collapsed holding pond and poured down 65 miles of the Powell River, smothering the riverbed and killing the host fish that the remaining mussel populations depended on to reproduce. Two rivers, two industrial disasters, one ecosystem broken at every level. What followed started inside a concrete hatchery building, with a fix so simple it seems obvious in hindsight, and ended with an ecological return that overshot the original damage by a factor of 57. The Clinch River, after August 1998, was not damaged. It was sterilized. Across that 7-mile corridor from Cedar Bluff to Richlands, the riverbed was bare cobble and empty gravel, with no biological activity of any kind. And the problem with that kind of loss, in this kind of river, is that it does not heal. Freshwater mussels do not migrate. An adult mussel spends its entire life anchored to the river bottom by a muscular foot, rarely moving more than a few centimeters in a year. It cannot walk upstream to fill a dead zone. It cannot drift downstream into one. It is too heavy, too slow, too locked in place. When a chemical spill sterilizes a 7-mile stretch, the gap it creates is functionally permanent. Upstream survivors cannot reach it. Downstream survivors cannot reverse the current. The dead zone simply stays dead. Now, a dense mussel bed is not just a population of animals, it is infrastructure. Each mussel pulls river water through its body continuously, filtering out suspended particles, agricultural runoff, and dissolved metals. Scale that across tens of thousands of individuals packed into the gravel, and you have a living water treatment system built directly into the riverbed. Their shells stabilize the cobble against flood scour. Their waste feeds the algal growth that anchors the entire food chain. When those 18,621 mussels died, the river did not just lose animals, it lost the machinery that kept the water clean, the gravel stable, and the food web running. And that machinery could not reassemble on its own. The mussels could not walk home. The fish they needed to carry their larvae had been knocked out of the adjacent Powell River 2 years earlier. The system was locked. The problem was not a lack of resilience, it was physics. Someone had to physically put the animals back in the water. And before anyone could do that, they had to figure out how to build them. By 2003, the federal government and the Commonwealth of Virginia had secured combined settlements totaling $5.4 million from the companies responsible for both disasters, the Certus tanker crash and the Lone Mountain coal operation. Unlike typical environmental fines that vanish into a general treasury, this money was legally ring-fenced. Every dollar had to go directly to mussel restoration in the Clinch and Powell rivers. No substitutions, no alternative uses. That dedicated funding built two purpose-built hatcheries, the Aquatic Wildlife Conservation Center near Marion, Virginia, and the Freshwater Mollusk Conservation Center at Virginia Tech in Blacksburg. Their stated goal was precise: rebuild what existed before the truck went over. Not improve, not partially recover, match the original. The thing is, you cannot breed these animals the way you breed fish. A freshwater mussel larva, less than a millimeter across, invisible without magnification, is a parasite. It physically requires a specific species of fish to complete its development. In the wild, the sequence works like this. A pregnant female extends a fleshy lure out of her shell, shaped and colored to perfectly mimic a crayfish or a small minnow, twitching it along the riverbed with lifelike precision. When a predatory fish, a darter, a smallmouth bass, strikes the lure, the mussel fires thousands of microscopic larvae directly into the fish's mouth and gills. The larvae clamp onto the gill tissue, feed off the fish's blood for several weeks, develop into juveniles, and then drop off wherever the fish happens to be swimming. That is how a creature that cannot move colonizes new territory. It hijacks a fish. Inside the hatchery, scientists cut out the randomness. They collected wild pregnant females from healthy, unaffected stretches of river. They extracted larvae under microscopes. They identified, for the first time, the exact host fish species required by each endangered mussel, a breakthrough the Certus settlement directly funded. They manually exposed tanks of those specific fish to the larvae, waited for the juveniles to develop and drop off the gills, and collected them from the tank floors. See, the problem was what came next. For the first 5 years, 2003 through 2008, the standard procedure was to release those juveniles almost immediately. Submillimeter animals, essentially specks, were poured into the river by the hundreds of thousands, and nearly all of them died. The current swept them off the gravel before they could anchor. Shifting sediment buried them. Predators picked them off. Establishment rates hovered near zero. Meanwhile, the exact chemical formula of Octocure 554 was protected as a trade secret, which meant nobody could confirm whether the riverbed itself was still toxic or whether the animals were simply too small to survive the force of the current. 1,350 gallons of rubber accelerant had killed 18,000 mussels, and now, 5 years and millions of dollars in, the replacement effort was dying on the same stretch of river. The breakthrough came around 2010, and it was purely mechanical. The hatchery teams stopped releasing microscopic juveniles and started growing them. They held the mussels in controlled flow-through tanks and outdoor ponds for 1 to 3 years, feeding them cultured algae until each animal reached 20 to 40 millimeters in length. At that size, when roughly a thumbnail, a mussel has a fully developed muscular foot capable of digging into hard gravel the moment it touches the riverbed. It has enough mass to resist the shearing force of spring floods. It is no longer a particle being swept away by physics. It is a functional animal that can anchor itself, filter water, and begin working from day one. That single procedural shift, from releasing specks to releasing animals, inverted the survival curve. At an average production cost of $14.75 per mussel, the hatcheries were now manufacturing organisms that could survive the river they were meant to repair. They had to solve an engineering problem before they could solve an ecological one. And once they solved it, the ecology started solving itself. Between 2003 and 2019, the two hatcheries produced 8.4 million juvenile mussels across 34 species. After the rearing shift, 127,574 of those animals, grown to stockable size aged 1 to 3 years, were deployed into the Certus impact zone. Thousands more went into the Powell River and into reinforcement sites over 40 miles downstream, insurance against a second localized disaster, wiping out the entire investment. What those deployments triggered was not a single recovery, it was a chain of consequences, each link crossing into a new domain. The first link was raw survival. Monitoring teams in dive gear mapped survey grids across the old kill zone and ran population counts season after season. By 2015, the data was unambiguous. The grown mussels were not just surviving seasonal floods, they were adding mass, laying down winter rings on their shells. A 7-mile corridor that had been biologically empty for nearly 2 decades had living animals locked into its gravel again. The second link was reproduction, and it arrived a few years later. Biologists conducting snorkel surveys documented something they had waited over a decade to confirm. Female mussels, hatchery-raised and never trained, were extending their fleshy lures in the wild. And then the proof that changed everything: untagged juvenile mussels under 20 millimeters showing up on the survey grids. No hatchery marks, no laboratory origin. Wild-born animals conceived and completed entirely within the river. The first generation produced without human involvement since before the spill. The system no longer needed the hatchery to sustain itself. The third link crossed into geography. During long-term monitoring, field teams noticed something that initially looked like failure. A large percentage of deployed mussels had gone missing from the survey grids. Only 15 to 43% of expected animals were appearing at the release sites. The first assumption was mortality, but the survival data at those sites was strong, and the numbers refused to reconcile. The answer reframed the entire project. The mussels had not died. Their offspring, hitching rides on host fish, had dispersed well beyond the monitoring boundaries. Populations were establishing over 40 miles downstream in Russell County, Virginia, with zero human assistance. The restoration had not just filled the dead zone, it had overflowed it. The fourth link was functional. As density climbed across the expanding range, the collective filtration started registering in the system. The river was not just reoccupied, it was operating again, cleaning its own water, feeding its own food chain, holding its own gravel against the current. What started as a targeted release at 2 sites in a 7-mile dead zone had become a self-replicating system operating across dozens of miles of river, running without a single dollar of ongoing human investment. The restoration was no longer a project, it was a process, and it was running ahead of the people who started it. The total ecological deficit from the 1998 spill was calculated at 52,940 discounted mussel years. A measure not just of the 18,621 dead animals, but of the filtration, the reproduction, and the habitat construction the river would never receive from them or their descendants. The 127,574 grown mussels placed back into the Certus zone, and the wild-born, self-replicating generations they produced are projected to yield 3,026,780 discounted mussel years. The restoration did not replace what was lost. It overshot the damage by a factor of 57, and the impact did not stop at the river. The accounting framework federal economists had built to quantify this recovery. The discounted mussel year, a unit representing the total ecological services one mussel provides across one full year of life, became the standard metric for environmental damage cases nationwide. The same methodology was applied to the DuPont mercury contamination in Virginia, calculating 650,000 lost mussels, and to the Ohio River case, which mandated replacement of 990,000 mussels by the responsible parties. A chain that started on a hatchery floor in Blacksburg was now shaping how federal courts across the country price ecological destruction. Put it this way. Those 3 million mussel years translate to over 18 billion gallons of autonomous water filtration pumped back into the upper Tennessee River Basin. No electricity, no chemical additives, no maintenance budget. A self-replicating system that repairs its own components, expands its own coverage area, and runs on nothing but river current and sunlight. The population models project it will keep operating until the year 2078, when the last cascading generational effects of the 1998 spill finally reach zero. 1,350 gallons of rubber accelerant sterilized one of the most biologically dense stretches of river in North America. The legal response was $5.4 million. The hatcheries produced 8.4 million living organisms, and the ecological return was 57 times the original loss, built animal by animal at $14.75 each. What the Clinch River proved changes how we think about fixing a damaged river. You do not repair it by cleaning it. You repair it by reinstalling the machinery that keeps it clean, and then stepping back. If you want to see more stories about how engineers, biologists, and sometimes the animals themselves are rebuilding broken systems from the ground up, subscribe